All right, welcome back. This is video number 3 of section 3.1, and it should be the final video for this section. The way I want to start today is to go back and look at example 5 from the previous video. I was really rushed at the end of that one because this recording program I'm using is allowing me to only record for 15 minutes at a time, and I was down to 14 minutes and 55 seconds, and so I kind of rushed through the last part of that last example there. So let's pick up down here where we're talking about the horizontal shrink, and I had put that it was times 2, but remember, whatever your b value is in front of the x there, you take the reciprocal of that, and that's the actual horizontal shrink factor. So really the horizontal shrink is not times 2, but it's by a factor of 1/2. So let's look at how that applies to our graph over here on the right. The basic points on any exponential graph, kind of your anchor points, are always 0, 1, because anything to the 0 power would be 1. And then 1, comma, whatever the base is. In our case here in this one, the base is e. So if I put in 1 for x here, I would get an output of e, which is approximately 2.7. So those are our two anchor points there. And then as these exponential functions have, it's a horizontal asymptote on the x-axis. So if you're horizontally shrinking it by a factor of 1/2, that means you're going to be multiplying all of the x values by 1/2. So this 0 here times 1/2 is still 0, so that point really stays in place. But this point over here, you're going to multiply this x value by 1/2 and get 1/2, comma 2.7. But remember as well, we're also reflecting it across the y-axis, so I'm really looking at negative 1/2, comma 2.7. Negative 1/2, 2.7. So your graph is going to be more steep than what I had originally drawn the other day, and that there would be your transformation of the original f of x equals e to the x. All right, so hopefully that clears up any confusion that you may have had there. Now, let's move on and talk about our last topic, which is the logistic growth functions. So with logistic growth functions, they are in this form right here. You have these 4 constants. They are all going to be positive, and b is going to be less than 1. B being the base if the function is in this format over here. A logistic growth function in x is a function that can be written in one of these 2 forms. So you can have it as f of x equals c over a plus a times b to the x, or what we will really be dealing with most often is one in this form over here. This constant c that is in the numerator of both forms is known as the limit to growth. All right, so let's just jump into one of these and see how we go about graphing it. We have f of x equals 18 over 1 plus 5 times 0.2 to the x power. Notice that all of the variable, or all of the a, b, c, and k are all positive, and this b value here is less than 1, which is what we are looking for. So first thing we want to do is find the y-intercept, and this works exactly like finding the y-intercept of anything else. You just plug in 0 for x, and 0.2 to the 0 is, of course, just 1. So really, I just have 18 over 1 plus 5 times 1. which is 18 divided by 6, which is 3. So we have a y-intercept at 0, 3 here. The next thing we want to look at is where the horizontal asymptotes are located. And those are always really easy to find. There are always 2 of them. The bottom one is always going to be y equals 0. And the one above that is always y equals the limit to growth, which is this number up here. So y equals 18 is going to be the other horizontal asymptote. And the reason why this is you can think about, as x gets very large, 0.2 to the x would be very small. So therefore, this number would be very close to 0, which means 5 times 0 would be very close to 0, which means you would just have 18 divided by 1, which is 18. So in other words, the bigger x gets, the closer this gets to 0, the closer the whole fraction gets to 18. So let's just draw in a horizontal asymptote up here at 18. And then, like I said, there's always one at y equals 0 as well. And then from there, just use what we were talking about here. We notice that as x gets infinitely large, the y value approaches 18. It'll always be in this kind of S shape like that. Mine's kind of wobbly, but you get the idea there. And you remember that S curve from a couple of chapters ago. That's one of our 12 basic functions. But this would be your basic shape here. If I ask you to describe the end behavior using limits, hopefully you could do that. We would say the limit as x approaches infinity of f of x is equal to 18. Just we talked about that, as x is getting bigger and bigger and bigger, the y value is going to be approaching this 18. As x is getting large and negative, however, the y value is approaching. See if you can think what you think that answer is while I'm writing it out here. Should have come up with the answer of 0 because I'm approaching this horizontal asymptote at y equals 0 here. Okay, let's look at another one. I believe this one is an application. Yes. So here we have a flu epidemic model. I give you this function here describing the number of people who have become ill with a flu outbreak T weeks after its initial discovery within a town of 64,000 people. So the first question is, how many people were ill at the beginning of the epidemic? Now notice that in this problem, T, which is the variable, represents number of weeks. So at the beginning of the epidemic, T is 0. So when I'm just asking you how many people were ill at the beginning, I'm looking for what would happen if I put in 0 in place of T. So in other words, let's just find f of 0. 64,000 divided by 1 plus 4,500. And of course, if you raise e to the 0, that's just going to be 1 because anything to the 0 power, rather, is 1. So this is 64,000 divided by 4,501. Put that in your calculator. I did it earlier. It turns out to be about 14 people. Remember, we're finding how many people were ill at the beginning. This is some sort of decimal, but we want to round to the nearest person rather than having fractional numbers of people here. So that's part A. Let's see, do I have part B on the next slide? I don't know. Yes, I do. Next question says, how many people were ill by the end of the 4th week? So there you're just saying what happens when t is 4. So let's just put in 4 in place of x, find f of 4. So that's going to be 64,000 divided by 1 plus 4,500 times e to the negative 1.2 times 4. Again, that's just a little calculator problem there. So if you put that into your calculator, if you have an old operating system, be very sure that you put all of this in parentheses. So you're going to have 64,000 divided by this entire quantity here. And that turns out to be about 1,682 people. And then the third question is, what is the limiting size of f of t? The population that can become ill. And so that is, hopefully you realize that if I were to graph this numerator up here, our 64,000 is that upper asymptote, and that is what the population that's becoming ill, that's what that is approaching. So our limiting size is 64,000 people. Okay. So I think that is the end of the lesson on logistic functions. Hopefully you can do those. And if you have any questions, feel free to ask the substitute or email me. I'd be happy to help you out. So I hope you have a good day, and you need to do the section 1 homework in the packet for tomorrow. Okay, I will talk to you later. Bye-bye.